तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So let us take up problem set 2 and go through these questions once again. This was just a bunch of objective type questions. The first one says the Lagrangian of a particle moving in a central potential V of r has two cyclic or ignorable coordinates, and remember the definition of a cyclic coordinate, something that does not appear, a generalized coordinate that does not appear in the Lagrangian at all. Is this true or false? It is false, and the reason is only one. Only the azimuthal angle phi does not appear. The theta appears because it appears as part of the metric in the kinetic energy. There are terms which involve sine squared theta and so on, and therefore there is only one cyclic coordinate in this problem.
Isn't it possible to construct a coordinate system without
Yeah.
one cyclic coordinate?
This is a very good question. Is it possible to construct a coordinate system such that there is a constant of motion corresponding to every cyclic coordinate, or vice versa? For every cyclic coordinate there is a constant of the motion. In principle, you see, the moment you have a cyclic coordinate there is automatically a constant of the motion, because the derivative of the Lagrangian with respect to the corresponding generalized velocity will give you the momentum, and that is conserved. This quantity is conserved. The question is, can we construct a coordinate system such that there is a constant of the motion corresponding to every cyclic coordinate? And the answer is, for a Hamiltonian system this is precisely what happens when you have an integrable Hamiltonian system, because you go to action angle variables in which all the angle variables are in fact cyclic coordinates automatically. So in that sense you have constructed a coordinate system, but it is not a global coordinate system, because when you go to an angle variable or an action angle pair, it is some function of the original q's and p's, and of course this is like saying that at every point I have a different change of variable numerically, in the sense that you have some function, and it is not a once and for all like going from Cartesian to polar coordinates or anything like that, but it is a change of variable. It is what is called a diffeomorphism at each point. So this is certainly possible, but then it is not guaranteed, not true for all Hamiltonian systems. Okay. For integrable Hamiltonian systems, for which the necessary and sufficient condition is that you must find n constants of the motion for an n freedom Hamiltonian in involution with each other. Okay. And there are deeper reasons as to why they should be in involution. Let me just mention that the fact is, we know that if you have bounded motion and it is an integrable Hamiltonian system, then you can change to action angle variables, and then the motion effectively takes place on an n dimensional torus. Now on an n dimensional torus, it is a very interesting topological object. You can always find, you need to find what is called a vector field which parallelizes this torus. In other words, you must have a basis, a set of vectors, unit vectors, which as you move along this torus would come back to the original orientation after any possible circuit. And this means this torus is what is called parallelizable in the sense of differential geometry, and the differentials of these n constants of the motion in involution form a basis. They are linearly independent of each other, and the only compact n dimensional manifold is an n torus, which is parallelizable, is an n torus. So this is the reason why the torus appears so naturally in problems of integrable Hamiltonians. Okay, so that is a little bit of technicality. In the next 4 or 5 parts, we have considered a Lagrangian, which is just a standard Lagrangian, which is 1/2 summation I equal to 1 to n mi ri dot squared, oh sorry, Ri vector dot squared the kinetic energy plus summation ij equal to 1 to n and I not equal to j, so that there is no self interaction. The potential is a function only of the distances between pairs of particles. Okay. This is a kind of, as you can see, general problem. When you have n particles, they interact with each other, they are non-relativistic, and the interaction proceeds by pairwise potentials such that the force between any pair of particles is directed along the line joining these two particles. That is all that it says. That is what this statement says here. Okay. Then the total angular momentum of the system is a constant of the motion. Is this true or false? It is true, because the entire system is invariant under rotations of the coordinate system. If I rotate the coordinate axis and move from any possible any set of orientations to any other set of orientations in this fashion, then this Lagrangian does not change, it is invariant. And by Noether's theorem one can then find constants of the motion corresponding to this set of transformations. This transformation is generated by 3 rotation generators, because they are in 3 dimensions. Correspondingly you have 3 constants of the motion, and they are the components of the total angular momentum of the system about an arbitrary origin of coordinates. Okay. So it is a constant of the motion. The next statement is, it is possible to make a Legendre transformation to the Hamiltonian in this case. Is that true or false? Well, it is true, because what you would require in general is that this Hessian matrix should be non-singular. And indeed that is true, because in the kinetic energy here all the different velocities are decoupled from each other. So imagine writing this as a sum of the Cartesian velocities for each of the particles. There are n particles and there are 3n such generalized velocities, and that matrix there is a trivial one. It is actually a diagonal matrix, because you can see there are no cross terms at all here. But yeah, qi dot, thank you. Yeah, it is qi dot qj dot, and those are these Cartesian components here. Therefore this is certainly possible. In this case it is completely trivial. Okay. We can find, by the way, in general, if you started with a set of particles and you impose constraints between them, various kinds of constraints, then in general what would happen is that this kinetic energy here, as you know from experience, is going to have coefficients, is going to be still quadratic in the general velocities, but it is going to have coefficients which would depend on the generalized coordinates. So the general form of kinetic energy T in such cases would be of the form Ij sum Aij qi dot qj dot plus summation over I some Bi qi dot plus some function C, where A, B and C are functions of the set qi and possibly time. If you have time dependent constraints, you put a particle on a plane like this and you tilt the plane as a function of time, then of course you can see that the independent coordinates would finally, the kinetic energy would look like that, but A, B and C would have functions of both coordinates as well as time. But the important thing is it would still remain quadratic in the generalized velocities in this fashion. Okay. But could have linear terms, could have a constant term as well.
What is the relation between two particles arise? As in,
Pardon me?
how is it that T is a function of, as in there is a term which involves the velocities of two different particles?
If they are connected to each other, if there is a constraint relating these two particles, then in general this would happen always. Yeah. There would be a cross term. They are still independent, these coordinates are still independent, but they are related to each other through some constraint equations possibly. Then in general the most general form you have is a matrix of this kind, a matrix Aij. There are other properties you can write down about this matrix, we will not go into that here, but then you must remember there could also be a linear term, there could be a constant term. You recall the problem of the bead on a hoop. There what happened was you ended up with just one independent coordinate, and that was the radial coordinate rho, but then you had a term which had form like half m omega squared rho squared. There was no, this was in the kinetic energy, and there was no velocity here at all, and that was an example of this point, the C here. And of course the rho dot squared, this term here, had a function of rho, a fairly complicated function of rho depending on the shape of this hoop, and that is an example of what A was.
C term comes because it's not Cartesian, because the coordinate system is not curved in some sense.
What's curved?
The coordinate system you're using, because
Yeah.
Cartesian, the C term won't be there.
Yeah.
And it
Oh yes, 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 of course. If you have purely Cartesian coordinates, this is not going to happen, but because we went in that case to cylindrical polar coordinates, and then the metric is not just constants. If you write the kinetic energy down, these are just constants here in Cartesian coordinates, but the moment you go to spherical polar coordinates or anything like that, remember you are going to get r squared theta dot squared, r squared sine squared theta phi dot squared, and so on. So automatically functions of the coordinates arise. Okay. The next one was, we can find capital N constants of the motion that are in involution with each other. True or false? In general false, unless you are given much more information about this potential. Trivial cases, if you switch off the potential, of course there is nothing there, it is immediately integrable. If this potential, can you give me an example of a potential where this would really be true? If you can find capital N constants of the motion, in fact there are 3n degrees of freedom here, and if the system is integrable, you can find 3n constants of the motion. Can you give me an example of when this, even with a potential, this problem would be completely solvable and integrable? What kind of potential would lead to this? Suppose I had a collection of harmonic oscillators. Suppose each particle was coupled to something else with a spring. This was quadratic, completely quadratic. What would happen then? Imagine, do this in one dimension first. I have a set of particles all on a line, and each particle is coupled by a spring to the next particle, coupled by a spring to the next particle, and so on. N of these particles.
Only to the next particle.
Pardon me?
Only to the next one.
Only to the next one. Let us say it is only to the next one. Would this be doable? Would this problem be doable? Yes, it would be doable. It is a quadratic Hamiltonian, so you can actually go to a set of coordinates where the thing would look, there would be cyclic coordinates. There is one cyclic coordinate here immediately which you can identify. I have n of these particles, 1 to n, coupled by springs, all of which let us say have the same spring constant k each, and let us do everything in the x direction. And what is the Hamiltonian of the system, or what is the Lagrangian of the system? This is equal to summation 1/2. Let us take the masses to be equal, simply to make life easy. I equal to 1 to n qi dot squared. Qi is the x coordinate of each of these particles, minus 1/2 m omega squared summation qi minus qj whole squared, ij equal to 1 to n. Of course I do not care, even if I equal to j, that gives you a 0, so I do not have to put this I not equal to j constraint. This system here, do you think this is integrable? Do you think this is doable? Completely quadratic Hamiltonian. Take two particles, take just two of them. So let us put capital N equal to 2, and they are connected by a spring. Could you integrate this problem? What would you do? 1/2 m q1 dot squared plus q2 dot squared minus 1/2 m q1 minus q2 whole squared omega squared. What would you do now? got two independent degrees of freedom, but they are coupled to each other by this spring. Now what would you do there?
So split it into the center of mass coordinate.
Yes, I would change variables to a center of mass coordinate because there is no external force on this system, and therefore the center of mass motion must be like that of a free particle with a mass equivalent to the total mass of the system. So what would I do? I choose new variables and immediately say let little q be q1 minus q2, the relative coordinate between these two particles, and capital Q equal to q1 plus q2 divided by 2. In this case, since they are equal masses, if they were unequal, what would I do? m1 q1 plus, can I only do m1 q1 plus m2 q2 over 2? Can't I do something else? Can't I do something else? Can't I do a linear combination? This is a good question. Why should I do q1 plus q2 over 2? In this problem, of course, once I do this, since the masses are equal, this Lagrangian would simplify, and what would it become? This would become 1/2 m q dot squared, total mass m q dot squared, and then what? Well, it will become 1/2 mu q dot squared, where mu is the reduced mass in general if I had two masses m1 and m2, and then it would have some spring constant times some constant minus 1/2 some lambda times q squared. It would look like this. In the general case, if I had two different masses m1 and m2, this is what it would look like. Capital M would be m1 plus m2, and little and mu would be what? If they are unequal masses, it would be m1 m2 divided by m1 plus m2, it would be the reduced mass, okay. And then what happens? Is there a cyclic coordinate? Capital Q is a cyclic coordinate, and what does that imply? Which momentum? Total momentum is conserved. Capital P, which is conjugate to capital Q, that turns out to be a constant of the motion. Little p of course is not a constant of the motion, there is a force, there is a relative force between these two guys. So you can change variables and get rid of one of these variables. What happens? Yeah. Pardon me? So put I less than j, okay. Then of course this won't happen. You sum over I and j and say take I less than j. Apart from some factor, this is certainly true, okay. So that problem is integrable when you have two particles. What happens when you have three? You can still do this. You can still do this. You can go to the center of mass that gets rid of one coordinate, there is one cyclic coordinate, and then two relative coordinates, say q2 minus q1 and q3 minus q2. You can still work with this. But coming back to my earlier question, assume the masses are all different, for instance, why should I choose this? Why should I choose in general m1 q1 plus m2 q2 over m1 plus m2? What happens if I choose some other linear combination? After all, I need two linear combinations. One of them is sort of dictated by the form of the potential, it is minus this, but the other guy could be anything else which is linearly independent. Some alpha q1 plus beta q2, I could choose that. What would not be a constant of the motion? The center of mass is not a constant of the motion. The conjugate moment, the total momentum is a constant of the motion. Yes, okay. So if I choose capital Q equal to some alpha q1 plus beta q2, what happens?
It will depend on the Lagrangian will also depend on.
Yes, yes. So it will turn out that the conjugate momentum is no longer a constant of the motion. In order to fix that, one chooses the center of mass. What happens if I choose 6 times m1 q1 plus m2 q2 over m1 plus m2? Some constant times that. Why should I choose 1 times that? Why not some constant times that? What would happen then? Your constant of the motion would turn out to be not the total momentum but some multiple of the total momentum. It turns out ridiculous to do that. So for convention you want it to be the absolute actual momentum, and that is the reason you choose the center of mass. So you ought to ask yourselves these questions all the time. What if I do this? What if I do something else? And so on. It is easy to go by a beaten path where people say do this and then do this. That is the algorithmic approach, but you should ask, suppose I do not do it, what happens then? So this problem with n masses and pairwise potentials of this kind is completely solvable. Gets much harder in 3 dimensions, we do not have nearest neighbor and so on, but the fact is once you have quadratic Hamiltonians then things are much easier to handle. Okay. The case n equal to 2 alone is integrable but not n greater than equal to 3 for a general V. True, because we know for n equal to 2 you can straight away go to the center of mass and relative coordinate and the problem is solved. The moment you have 3 or more, for an arbitrary potential this is no longer true, for a general potential. Is it true if you had 3 particles interacting with each other pairwise but by the Kepler potential, 1 over r potential, say gravitational potential between 3 particles? Is that integrable? It is not integrable, famously not integrable. 2 yes, the 2 body problem is solved, but 3 no, in general no. There are special cases which could be integrated, but the fact is in general for arbitrary masses this is not true. This is the famous 3 body problem which people spent a lot of time, and eventually Poincaré I think established that it is essentially not integrable, it is not a solvable problem. There are 3 cyclic or ignorable coordinates in this system, true or false? This system. Why do you say that? Why do you say that? It seems to me that if I go to the center of mass system, the center of mass coordinate, which is a vector, is actually a cyclic coordinate. So there are indeed 3 cyclic coordinates in this system, the center of mass coordinates. They do not appear in the Lagrangian because the Lagrangian depends, the potential depends only on, I write a plus here, it is a minus. The potential depends only on the relative distances between particles, and therefore the total center of mass coordinate does not appear anywhere in the Lagrangian. Okay. By the way, if you have more than 3 or more particles, then it is not always the best choice to choose the relative coordinates always. If you have a potential of this form, it is naturally dictated, but in general if you got a 3 body problem or a 4 body problem and so on, there are other choices of coordinates, there are Jacobi coordinates and so on, which could be more efficient in certain instances, but getting rid of the center of mass is always a useful thing to do because that gives you 3 cyclic coordinates right away. An n dimensional dynamical system is given by x dot as gradient of phi, but it is a gradient system. If del squared phi is less than 0 everywhere, then the system is conservative, a conservative dynamical system. True or false? It is false. In this case in fact you would like to have del squared phi equal to 0, then in the standard definition of a conservative system the vector field has vanishing divergence and then it is conservative. Let h of qp be the Hamiltonian of an autonomous system with 1 degree of freedom. If a of qp is any function of the dynamical variable such that the Poisson bracket a with h is 0, then a is either a constant or a function of h itself. True or false? 1 degree of freedom, just 1 degree of freedom. It is an autonomous Hamiltonian system, therefore how many independent constants of motion can you have? 1, the Hamiltonian, that is it, time independent constant of the motion. So it says if a with h is 0, then a is either a constant or a function of h itself, and that is certainly true.
If two of them are functionally independent, does it mean that one is a function of the other? Functionally dependent?
Yeah.
Like if I have some y square plus x cube equal to constant,
yeah.
you can't explicitly get a function of y
not necessary, but definitely they are related to each other. Yeah.
So you can't say it's a function of h, you can just say it's functionally related to h.
It is a function of h. I may not be able to invert it uniquely at all points, but it is a function. certainly true. May not be a single valued function everywhere, but it is certainly true. Is this true, by the way, if you had more than one degree of freedom? Is this true if you have more than one degree of freedom? Not true, not true, definitely not true. So you can't make a statement of this kind. It could be another constant of the motion which is in involution with this. Incidentally, a related question, if Poisson bracket of A with B is 0 and A with C is 0, is a Poisson bracket of B with C 0 necessarily? Not necessarily true. Again, if it is all 1 degree of freedom, then this whole thing reduces. We know that B and C would be functions of A anyway, of the Hamiltonian. So not true in general. The critical points of an autonomous Hamiltonian system can only be saddle points and centers. That is true because this is a conservative system. For a Hamiltonian system, there are no attractors in phase space, no limit cycles, no strange attractors, and no critical points which are asymptotically stable and so on, no spiral points, etc. You can have saddle points, you can have centers, and then you can have more complicated kinds of behavior. You could have a chaotic behavior, completely chaotic behavior, but you would not have these so called strange attractors which exist in dissipative systems. They do not exist in Hamiltonian systems. Okay. A particle moves on the x axis in a potential k mod x to the alpha, where k and alpha are positive constants. All the phase trajectories are closed trajectories in the xp plane. True or false? This is true. This is like a bounded potential which is going up in some fashion, and all physical trajectories are closed trajectories. And continuing, the time period of oscillatory motion of the particle is independent of its total energy in the cases alpha equal to 2 and alpha equal to -1. In other words, you are told if the potential is kx squared, then the time period is independent of the energy, and the case alpha equal to -1, that is k over x, and that is not true necessarily. This is not so. X squared is true, yeah. X minus 1 is not true. X minus 1 is not true. What about x minus 2? What about x squared plus 1 over x squared? What about x squared plus 1 over x squared? Well, that is an interesting problem. It actually takes us on a field to something totally different. Look at that potential. A is a positive constant, Ka positive. What is the shape of V of x? Yeah, it will be 2, it is going to be infinite here, so it goes off like that parabolically, and then it is infinite here, it goes off like that parabolically on this side, they are symmetric completely, and you can have periodic motion in either of these two potential wells. So the question asked is the time period for this motion the same as the time period for that motion? Of course you have by symmetry exactly the same sort of motion possible here. Remarkably enough, the answer is yes, the time period for this motion is independent of the amplitude, even though it is not a harmonic oscillator potential. This is called an isospectral isochronous potential. It has got exactly the same behavior as the harmonic oscillator. And if that is the case, then what should the time period be? It would be exactly the same as if this were not present at all. So the time period in this problem is independent of A. I want you to work this out. Okay. It can actually be done. Write down the time period, it is not hard to do because you know the Hamiltonian, you know the phase trajectories, and you know what it is completely symmetric motion. So you can actually find out what the time period is. What you need to do is to take some turning point here and turning point here for a given value of the energy and integrate to find the time period, which takes is twice the time it takes to go from here to there and back to there, and you will discover that this integral is actually independent finally of the position of these turning points and depends only on this constant k. So it is a remarkable fact that you have a whole family, because now I can change a, it is a parameter, and as I tune a, the time period remains independent. This is the starting point of a whole series of investigations, because you can make the potential more complicated. This is part of what is called the Kalergero-Sutherland model, and then from here you go on to the quantum version. Then you can put all these potentials on a line, pairwise potential, and integrate, and from there you get other integrable models and so on. So there is a huge field of study devoted to integrable models. It starts with this very simple example, and when you quantize this problem, then you have again a situation where you have harmonic oscillator like behavior, which means the energy levels are equally spaced. So you have non-quadratic potentials for which the energy levels are equally spaced, and they are called isospectral oscillators. So there is a huge field of study associated with this apparently simple problem here. Once again, what would you guess is the reason why this thing becomes independent of A? Take a guess. Well, there is no quote unquote deep reason in that sense that I expect of you, but what would you think is, what is the mechanism by which this is happening? It would imply that you can go to some new set of coordinates, you can make some change of variables such that it looks like a harmonic oscillator, right. So that is eventually what happens. Okay. Now the next one was consider an autonomous 4-dimensional dynamical system where x is and f are elements of R4. This system can have at most 3 functionally independent constants of the motion that do not have any explicit time dependence. True, this is certainly true, this is just a general statement. Continuing, this system can have at most 4 functionally independent constants of the motion, of which at least one must be explicitly time dependent. Also true. The product of all the eigenvalues of any rotation matrix in n-dimensional Euclidean space must be equal to -1 to the n. False. What should the product of all the eigenvalues be? +1. For proper rotations it should be +1, because these are orthogonal matrices and they are connected to the identity, and therefore the determinant is +1. A system consists of n particles moving in space under k integrable constraints. Some of the constraints may be time dependent, and the question is, the number of independent generalized coordinates of the system is 3 times n minus k. What is it equal to? It is 3n minus k, not 3 times n minus k. Good. The kinetic energy of the system in general is of this form that I wrote down there. Is that true or false? Where n is the number of independent degrees of freedom, aij, bi and c are functions of q's and t's. I already said that is true, so this is certainly true. A particle moves in space under the potential k times x4 plus y to the 4 plus z to the 4, where k is a positive constant. This looks like a harmonic oscillator potential, but it is not, it is 4th powers. The angular momentum of the particle about the origin of coordinates is a constant of the motion. Why is it false? It is not rotationally symmetrical, it is not invariant under rotations. It is invariant under a set of transformations which would exchange the x, y, z axes, in other words 90-degree rotations about the 3 axes, but that is a discrete set of transformations. It is called Cartesian symmetry, you can exchange y for z, z for x and so on and so forth, but this is not the same as a continuous set of rotations. And therefore this problem, the angular momentum about the origin is not constant in this case. The next one is a particle moving in space under the potential V of r, and this is not a central potential, it is a function of the position itself. If V of r is invariant under the parity transformation r to minus r, this implies the existence of a constant of the motion according to Noether's theorem. It is also false, because this is again a discrete transformation and you do not have a Noetherian current associated with it, and therefore there is no such requirement. I should mention here, and we are going to talk about symmetries later on in the course, that there are other sources of symmetries. There are continuous sets of transformations, then there are discrete symmetries like parity or maybe time reversal invariance and so on, and then there are other symmetries which are not induced through changes of coordinate systems. Rotations, translations and so on would be things you do to the coordinates, but you could have other symmetries which have nothing to do with the coordinate system, like a gauge transformation on electromagnetic potentials. Those transformations could also lead to symmetries, they could also lead to conserved quantities, equations of continuity and so on, but they have nothing to do with coordinate transformations. And finally there is another source of symmetry in nature, and that is there are topological symmetries. There are topological conserved quantities. There are some conserved quantities which would be completely topological in nature, they have to do with the nature of the space that you are in and nothing to do whatsoever with space-time transformations or anything like that, and I will mention that when we come to it at that stage. Once again, applying Noether's theorem in those cases is not immediately obvious valid. So a simple example would be, let me just give an example so I do not mystify you. You take a long string, a very long string, and you put a knot on it. Now obviously you can move the knot around, but it is there somewhere. In some sense the fact that you have one knot on it continues no matter what you do, no matter where you move, unless you do something drastic like you go to a finite endpoint and remove it, or if you go to infinity, or if you cut the string. If you do not do those things but you take a long circular piece of rope with the single knot on it, no matter what you do there is always one knot on it, and that is a topological fact which you can't get rid of. Okay. The next one was the canonical momentum of a charged particle moving in an electromagnetic field is dependent on the gauge chosen for the electromagnetic potentials. Yes, this is in fact true. This is in fact true. Okay. The dynamical symmetry group of the n-dimensional isotropic harmonic oscillator is SO2n. It's SUN. It's actually SUN and not SO2n. How many generators does SO2n have? 2n times 2n minus 1 over 2, that is n times 2n minus 1. And how many generators does the symplectic group of this problem have? There are n degrees of freedom, so it's n times 2n plus 1, that is the number of degrees of freedom. So that is a larger group than the group of rotations. And how many generators does SUN have? N squared minus 1, it is a much smaller group. So the symmetry group is the intersection of the symplectic group sp2n with the group of invariances of the Hamiltonian, which is SO2n, and that turns out to be SUN, a much smaller group. As I said, we will talk about these groups towards the end of the course. Okay. A system has 2 degrees of freedom, the Lagrangian is q1 minus q2, q1 dot minus q2 dot squared plus an arbitrary potential. It is not possible to make a Legendre transformation to the Hamiltonian in this case. True or false? It is true, because this Hessian matrix becomes singular in this problem. So here is a case where you can't do it. There is no way of going to a Hamiltonian in this system. Okay. The remaining questions were groups on the symplectic matrices. The group of 2n by 2n symplectic matrices with real elements is a subgroup of the group of 2n by 2n orthogonal matrices with real elements. That is not true, we just found out that SO2n is actually smaller than sp2n. So, okay. M denotes the Jacobian matrix of a canonical transformation. The transformation whose Jacobian matrix is given by M transpose is also a canonical transformation. True, true, because remember M transpose is related to M inverse and a canonical transformation is invertible. So it is certainly true. And what is the definition of a symplectic matrix? You must have M transpose Jacobian M equal to J on this side, and it is easy to show from here that M inverse and M transpose are both also symplectic transformations. Noether's theorem, and this is an important statement, Noether's theorem enables us to find a conserved quantity associated with a group of transformations of the dynamical variables of a Lagrangian system, continuous transformations. The statement is, in order for the theorem to be applicable, the Lagrangian must be unchanged under the transformations belonging to the group. Not in general, not in general. Of course if it is unchanged you end up with a conserved quantity, okay, but in general what can happen? The total derivative of a function of the coordinates and time could be the change. Now what is the implication? What quantity is unchanged? The Euler-Lagrange equations are unchanged, but as a consequence of what remaining unchanged? What is it that remains unchanged? The action does not change, the action is invariant, right, and therefore this is certainly true. In fact, this is important. There are instances such as the gauge transformation on the electromagnetic potentials, where we saw that the Lagrangian changes precisely by the total time derivative of a function of the coordinates and time, and you still have a conservation law, you have the conservation of charge. Okay. There is an analog of the Laplace string length vector, namely a vector constant of the motion, for the motion of a particle in any central potential of the form V of r is kr to the n. Not true, not true in general at all, there is no such thing. What is true is that if you have an r squared potential, the harmonic oscillator potential, then there are other constants of the motion, that is an integrable system, that is super integrable in the sense that you have a symmetry group which is a large symmetry group SUN in the case of the oscillator, or in 3 dimensions it would be SU3. Now that quantity is not a vector. The constant of a motion for a 3-dimensional isotropic oscillator is in fact this quantity Qi Qj plus Pi Pj, and that is a tensor of rank 2, and you put I equal to 1, 2, 3 and you have all these quantities and their constants, all the components, they are not all independent of each other, some would be related. For example, the trace of this guy would be the Hamiltonian itself and so on, but you have this tensor constant of the motion because of the symmetry group that is involved. So this statement is not true, but what is interestingly true is that, and this is a theorem that has been proved many years ago by one of our best mathematical physicists N. Mukunda from the Indian Institute of Science, he proved that for a central potential of this kind, locally at each point in the phase space you can find a change of coordinates such that the problem has either the symmetry of the Kepler problem or the symmetry of the oscillator locally. But of course if you could do it globally everywhere with the same change of variables, then the problem is integrable, which it is not in general. But what is interesting is that you can show in 3 dimensions when you have a central potential, locally you can map the problem on either to the isotropic oscillator or to the Kepler problem. It is an interesting result. Okay. Euler's equations of motion for the force free motion of a rigid body describe a completely integrable system. It is true or false? This is true. This is true. The equations of motion, in fact we saw the constants of the motion also, and you could write down the trajectories which are on a sphere. Okay. The next one had to do with fill in the blanks, and most of these are standard problems here, so let me not go through this. There is a problem here which we did not talk about earlier. Let us do that, let us look at that, because there is a problem which we did not mention, and I did not talk about this at all. We switched horses a bit, it is x plus y minus x times x squared plus y squared, and y dot equal to minus x plus y minus y into x squared plus y squared. Okay. And it talks about the Bendixson criterion, which I did not mention in class, which I did not yet talk about, but let us look at this 2-dimensional dynamical system. The first question is, where are the critical points of this system? Well, the origin is clearly a critical point of the system, so let us see what kind of critical point it is at the origin. And what you do of course is to neglect this and just look at this portion, that is the linear portion of it. So the linearized version, the linearized one is x dot y dot equal to this matrix L, which in this case is 1 1 minus 1 1 on x y. This is the matrix Y, linearized gives you this matrix here. What kind of critical point is it? Well, we need to know its eigenvalues. So let us find what is its trace and what is its determinant, and that should tell us immediately what happens. So the trace t equal to 2 and the determinant delta is equal to, okay. Therefore what sort of eigenvalues do you have? Pardon me? Complex. So lambda 1 2 equal to 1 plus or minus over 2 or 1 plus or minus I, that is it, okay. Therefore what kind of critical point? It is an unstable spiral, things are going to flow away from it, okay. And the question is, where are they going to go to? Because my argument is the following: I look at the phase plane and I know this is an unstable spiral, but if I look for example at this point here very far away, large x and large positive y, then this is a negative term and that is a negative term. So both x and y are decreasing. I should really be coming in if I am way out here, and yet this is unstable, it is flowing out. How could you reconcile these two statements? From the origin things are going to flow out, and if I am sufficiently far away I am going to flow in, unless there are other critical points. Are there other critical points in this problem? 1 0 0 1. Let us look at this system in polar coordinates. It suggests that we should look at it in polar coordinates because you have this here, this present here, this non-linearity. Maybe we will be able to handle it exactly. So let us go to polar coordinates. I put x equal to r cos theta and y equal to r sin theta. Then how do I find r dot? I would like to find r dot and theta dot. What do I do? So I have r squared is x squared plus y squared. This immediately implies that if I differentiate r dot is xx dot plus y dot. Just differentiate both sides with respect to time. So what does r dot become in this case? I multiply by x dot here, so let us do that here. It is xx dot, so it is x squared plus xy minus x squared r squared plus y dot, so there is a minus xy plus y squared minus y squared r squared. So this term obligingly cancels out and you get r squared minus r4 1 minus r squared. So we have r dot in this problem is equal to r times 1 minus r squared. Okay. So this actually suggests immediately that if r is sufficiently large, bigger than 1, then you know immediately there is a circle here at radius 1, and if you are outside the circle then r decreases because r dot is negative and therefore things must flow in, but if you are inside this circle it must flow out because 1 minus r squared is positive. In which direction is this going to happen, clockwise or counterclockwise? This depends on what theta dot does, but what is theta? Theta is equal to tan inverse y over x, and therefore theta dot equal to, if I differentiate this, 1 plus y squared over x squared, and then the derivative of this guy which is y dot over x minus y over x squared x dot. I differentiate y over x with respect to time and I get two terms of this kind. So this could be written as equal to, and the x squared cancels out and you get xy dot minus yx dot divided by x squared plus y squared. Now that is a useful formula. That is the way theta changes, and let us find out what theta dot is in our problem. So theta dot is equal to xy dot, so I multiply this by x, minus x squared plus xy minus xy r squared, and I subtract from it yx dot, so minus xy minus y squared, is that correct? Is this correct? Plus xy r squared plus xy r squared, and that's got to be divided by r squared. Is this correct? Pardon me? Yeah, so that's minus 1. This term cancels out and that's equal to minus 1. That says that you are going to move in the clockwise direction. So this immediately says that if you start here, you are going to spiral out in this fashion and approach this trajectory. By continuity, this trajectory also moves in this fashion, because if I set r equal to 1, I start with r equal to 1, any point on the unit circle, I am just going to keep going around it in this fashion, and if I am anywhere outside there, I am going to spiral in and fall into this circle here, and this trajectory therefore is a very special trajectory, and this is a limit cycle. So this problem actually has a very different kind of attractor. There is an unstable spiral point at the origin, but then it ends up, the stable thing is, the stable attractor is not a fixed point, it is not a critical point, but rather a whole trajectory, a one dimensional object, and it is a limit cycle, it is an isolated periodic trajectory. It appears limit cycles occur only in dissipative systems, not in Hamiltonian or conservative systems. And it is clear in this problem the phase space volume elements here are all shrinking, and they are finally going to end up on this line, and volume elements here are also going out and going to end up here. Every point other than the origin inside the unit circle is going to finally end up asymptotically approaching this limit cycle, and from the outside too. I think I have run out of time. Somebody had a class today, so we will stop here and then we will take it up the next time. I would like to move now to slowly towards statistical considerations, which is what we will start with next week. Meanwhile, if there are other problems here which if you have any questions on them, let me know and we will work those problems out explicitly. I did think in terms of writing out the solutions and sending it to you by PDF files, but I thought that would be a little too much to do this, so I am not going to do that. If there are questions, I will answer them. Okay, this is fine. Yeah. Okay, let me stop here.